There's no getting around learning Boolean algebra, but it's not as hard as people make it. So let's go ahead and let's write out what our rules of Boolean algebra are. So we've got A or 0 equals A. 2, we got A or 1 equals 1. 3, we've got A and 0 equals 0. 4, we got A and 1 equals A. 5, we've got A or A equals what? A. Number 6, A or not A equals 1. Okay. 7 is A ANDed with A equals A. 8 is A ANDed with not A equals 0. 9, A double not. So if we invert invert is equal to the original, right? 10 is A or A and B equals A. 11 is A or AB equal, or A not B, sorry, A not B equals A or B. 12 is A or B. And when we do the parentheses, we're ANDing, like think of multiplication as ANDing, okay? Because when we get going, an OR gate will add numbers and an AND gate will multiply numbers, okay? That's going to be pretty valuable later. A or B ANDed with A or C equals A or B, C. Okay? Now, everything above this line should be very easy to catch. Okay? Everything above 10 should be super simple. I'm going to be very quick on these. All right? If you OR anything with a 0, if this is a 1, that's going to be a 1. So if it's a 0, it's going to be a 0. So anything you put in here is going to come out here, right? So if you OR something with a 0, it's going to be that same thing, okay? So, do what? Yeah, so if I have an OR gate and I have this line and it's got a button on it, right? And I OR it with 0, that output is going to be equal to whatever that button is, okay? So when we're talking about simplification, why do I even need the OR gate? All I need is that button, right? Right? So if I have a big complicated thing and part of it's, this ORed with 0, I don't even need the OR gate. I just run that line out, okay? A ORed with 1. If we've got a 1 on any input, it's going to be a 1, correct? So everybody's got that, right? Everybody's got number 2. Everybody got number 1. Everybody's got number 2. If there's a 0 on the input of an AND, it's always going to be a 0. So if we don't care what goes on before it, if it gets there and it's ANDed with a 0, I can ignore everything on the other side. The output's always going to be 0. A ANDed with 0, it's always going to be 0. A ANDed with 1. Now that gives us a question. Like, if it's ANDed with 1, that 1's not automatically making it one thing or another, right? The 0 automatically makes it a 0 on an AND gate. A 1 on an OR gate automatically makes it a 1 on an OR gate, right? So when you AND anything with a 0, you get a 0. And anything with a 1, we've got more information we need, right? So if the A is a 0, it's going to be a 0. If it's a 1, it's going to be a 1. A or A equals A. So if we have a big long thing and we wind up where both of those wires are tied together, right? We don't need the OR gate. If that was a 1, we'd have 1 on both of them. If it was a 0, we'd have 0 on both of them. It's going to follow what A is. A or not A. So we've got A going into an OR gate. And then we're coming out and we're inverting one side. That's always going to be 1. Because if I've got a 0 right here, it goes through that knot and it gives me a 1. If I've got a 1 on the OR gate, it's a 1. If I've got a 1 here, this one takes care of it. Right? Everybody good there? A ANDed with A is A. Makes sense. If that's a 0, it's 0 on everything. If it's a 1, it's 1 on everything. Wait. Yeah. A ANDed with not A is always going to be a 0. So the opposite of what's going on with the OR. It's always going to be 0. Because if this is 0, it already kills this AND gate. If it's a 1, the inverse of that is going to kill the AND gate. Everybody feel good about the ones we've done so far? We good? A double knot. When we knot something, we get the opposite of it. So if we've got a 0, we got a 1 right here. If we put it through another NOT gate, then we get a 0. If we have a 1 going in, we get a 0 right there, we get a 1 going out. So if we invert something twice, it's back to where it started. So those were pretty easy, right? All right, so let's say that if you read the chapter and you pay attention right here, these are the only ones that you should really have a problem with. Is that a fair assumption? Okay. Let's say I have 2 doors. Okay? I can go through one door that I have to give it my name. And I can go through another door and I can give it my name and my social security number. I can get to the other side of those 2 doors with just the one that does my name, right? All right, so when we have an A or an A and a B, it's just going to be what A is. If A is 1, it's already going to trigger that OR gate to be a 1. If it's a 0, it's not going to trigger right there, and it's going to turn off the AND gate, so I can't get through it. Okay? The AND gate makes it more complicated to do. But the AND gate is dependent upon that A to do what it wants to do, right? So when we have something that is dependent upon something that is taken care of by an easier path, right? Then we can kind of ignore this part right here, okay? Because on that part, we still need an A and a B to actually make that work. And we need A to be 1 right here, but if we've got 1 up here, right? That's part of the simplification, right? Like we had 2 gates, and now we only have a line there, right? We just have a wire. Because as complicated as that was, because if we had AB, we would already have A to unlock the OR gate, right? Cool. All right. Do y'all think y'all got 10? Can I take that off of the question mark list? All right. Now let's get into some funky. Now I hope that drawing it out at this point might start helping y'all visualize what's going on. I've got A OR, A not B. Can y'all visualize when you draw it, like how things turn on and off? All right, so let's prove it on a just a math level. We've got that big circuit, and then we've got this circuit right here. So let's make a truth table. Do y'all know how to make a truth table? You should. All right, so the truth table for this right here, let's say AB, and then we've got Y. Let's say Y is coming out. If we've got a 0, or if we've got a 1 on any of those inputs, we've got a 1 on the output. So that's the truth table for A or B. Okay? Now let's do a truth table over here for A or A not B. Okay, so 0, 0. We've got a 0 right here. We've got a 0 on B, so that kills the AND gate. We don't even have to care about the inverter right now. We've got a 0 here, don't we? 0, 1. I've got a 0 right here, so that's not helping. But then that gives me a 1 right here, and I've got a 1 with the B. That does help, doesn't it? So now that AND gate opens up. We get a 1. All right, 1 and 0. Well, that 1 right there, boom, boom, boom. We don't have to look any farther, do we? So there. And if we have a 1 on the A, we don't have to look anywhere else, do we? Do those 2 truth tables hold? Okay. So let's make it make sense. Like y'all know, all right, we went to Huntsville and we watched, you ever watch Smarter Every Day, like the YouTube channel? The guy who does that is from Huntsville, or he's from Alabama. He's a genius, but we went to the STEAM Fest, which was like science and astronauts and cool things. And he was the keynote speaker, and he was talking about knowing something is not the same as understanding something. Like you might know how to ride a bike, but you don't understand how you ride that bike. Right? So right now we understand that this is true. but let's make sure that we understand why it's true. Okay? You understand that it's true, but let's understand how it's true. Let's look at those two separate things as separate. Okay? A or A not B. Okay? If we've got an A, we've already got our thing, right? So if any A is 1, we've already got it. Okay, so that's one part of that second equation. Or B. If we've got a B, then either A is 0 and the A is getting inverted and turning into a 1 to give us that AND gate, or it's a 1 and it bypasses everything and it gives it to us through the OR, right? So if I have a 1 right here, it doesn't matter what this A is. If it's a 0, that becomes a 1, which opens up this, right? If it's a 1, that's just straight through there. So if we have a B, it doesn't matter what A is. And if we have an A, it doesn't matter what B is. Okay? Now look at our truth table. And it holds that out. Right? What is A? A is these right here. If we've got an A, we've got 1s. Or B. So this one and this one. So if we've got a B, we got those two. Now we've got some overlap, but that doesn't matter. Like A or B is going to open it up. Okay? Y'all feel good about 11? Okay. And 12 is the last one. And like with those 12 rules, which to me, about 9 of them are pretty self-explanatory. We're getting there. A or B ANDed with A or C should equal A ORed with B and C. Okay? Now, this one was the one that gave me headache. And it might still be the one that gives you headache. But I hope that I can help not make it. Now, we're going to prove this with 2 truth tables. All right? But let's see if we can work it out with our brain a little bit. Okay, so your book actually says that it's the distributive law, right? Like when you're doing math and you distribute things out, right? Now they give you postulates where they make you work it out and, you know, break it down and do stuff like that. But let's see if we can't come up with it in our head where it makes sense as opposed to like breaking it down into rigid algebra. Okay? Yeah. Yeah.
B are correct, it doesn't matter because these are correct. That's why B and C have to be both correct for it to matter for this.
Yes. Perfect. Okay. So it might be hard for them to hear you on the video because like I have to have my fan on, so I have to filter out everything that's not my big old mouth talking. So I've got like a cone like right here. Yeah, but I want the world to know that you got it right. All right. So what Adam said was A is super powerful. Okay? Like if A is true, then it triggers both of those OR gates, which triggers the full AND gate, right? If A is not true, then we have to have a more difficult way of getting a true on both of those, and in which case B and C both have to be true because we need a 1 on each one of those OR gates. Okay? So, yeah, you distribute it out, but what it comes down to is when you have a variable in multiple spots, then that's a lot more powerful of a variable. Okay? All right, so if A is true, we're golden. If A is not true, then we have to do a little bit more complicated of a thing it makes it a little bit more complicated for that to be true. B and C both have to be true for that to be let out. Okay? So those are the rules of Boolean algebra. Okay? Now, there's one other key component to being able to make a really big circuit into a small circuit, and that's De Morgan's. And this was my Moby Dick. This was my big old whale that I could not get my mind around. And once I did, yeah. All right. So De Morgan's basically says, let me read it out to you. The complement of a product of variables is equal to the sum of the complements of variables. A complement means an inverse, okay? A sum means an OR, and a product is a multiplication or an AND, okay? So what it's saying is the sum, the OR of complements is equal to the product complemented. And then you flip that, and like, so if you have the product of complements, then that's equal to the sum or the complement of the sum of those product or of those inputs. So we can go from this right here back and forth, right? Or we can go from like the product of complements is equal to the sum complemented. Okay. OR gates are like addition, AND gates are like multiplication. We're going to prove that. All right. That's going to blow your mind. So let's prove this real quick. Okay. Let's do some proof. All right. So we're going to say that if we have an inverter and an inverter on the inputs, whatever gate right here is going to equal the opposite gate with just one inverter on the output. Okay? If y'all want me to prove it twice, I will, but I'm just going to prove it once, and then you can ask me to prove it the other way around or whatever. But let's do a truth table for these two things, right? We've got two inputs, so we've got 4 different combinations that we can do with them, right? let's say that's Y and that's Z. I need y'all to get used to having multiple outputs because we're about to do some cool things. All right, so if it's 0, 0, if it's 0, 0 right here, it becomes a 1, 1 on the AND gate, right? And that becomes a 1. Correct? So for Y, that's a 1. If we've got 0, 0 on the OR gate, we get a 0. We complement it, we invert it, and we get a 1. It's looking good so far. If we've got a 0, 1, we get a 0 here, which means a 1 here. We've got a 1 here, which means a 0 here. That's going to be a 0, isn't it? We get a 1, 0. We get a 1 here because we've got a 1 on the OR gate. We complement it, and we got a 0 here. Now, what I want you to do is realize that if I have a 1 on either one of those inputs, I'm going to get a 0 out, ain't I? That's the important thing to note. If I've got a 1 on either one of those inputs, I'm getting a 0 out. So I can fill the rest of these out, can't I? And they look exactly the same. Why does this matter? Right here, we saved one gate. We've got 1, 2 gates. We got 1, 2, 3 gates. But what if we had this big honking AND gate and let's say it had like 10 inverted inputs, right? Now, we just show that with a little dot, but those are actually gates. Those are like inverters, right? We can replace that with one OR gate with all the inputs with one. So like as we get bigger, we change it by magnitude, correct? Now, it also is easier to understand this one right here than it is this one right here. Because if we have a 1 on any of these, we're getting a 0 out here, don't we? So y'all see where simplification, this is how we're going to simplify circuits. Okay? All right. So one of the things I want to do is I'm adding the De Morgan's part of that. So if you did it through that chapter, like I had did specific ones for last week out of 2, and I left out like one section in De Morgan. So if you did those 2, like just take that stuff over. And I also did a video which is explaining De Morgan's a little bit better than I did here, right? But it should be up now. Okay. All right, so you need to be able to go from truth tables to equation forms to schematic diagrams back to truth tables, and all of those should be connected. Okay. Like if I gave you a truth table, you should be able to make an equation out of it. If I gave you a schematic, you should be able to make a truth table out of it. Okay? Like we should be able to do all three of these things. All right, so if I write a letter, that is it uncomplimented. Okay? If I write a letter with a little line over that, that's that inverted. Okay? If I write the letters beside each other, they're anded together. If I write variables beside each other with a plus sign, they're ORed together. Okay? So let's go from a truth table to a equation real quick. I've got 3 variables, so I've got 8 different combinations. Okay? I want y'all to tell me what the output's going to be. We're making our own circuit. We need it to do a certain thing. Let's say we've got a counter, and it's counting from 0 to 7. Okay? So then we want the light to blink at certain numbers. All right, we want it to do certain things at, like, let's say 3 and 8, or 3 and 4 and 7. Okay? So I don't want y'all to think that I memorized this, so y'all tell me what you want to be ones in here. Where do we want, like, this is an arbitrary circuit. Okay, we're making a circuit. When do y'all want ones? Let's make it 1 when the input's 1. So we've got 0, 1, 2, 3, 4, 5, 6, 7. Does that work? And then let's say that 4, 5, and 6 are ones also. Okay? So we've got something that looks like that. Okay? Easiest thing is to look at when it's true and just put those things together. All right. So it is true when A is 0, B is 0, and 1 is, or A and B are 0 and C is 1, right? So let's draw that. We're going to do both. All right, so A is 0, B is 0, but C is not. Okay? Cool. It is also true when A is 1, B and C are 0. Now, y'all know how that works, right? Like if I've got a 0 and I want to turn on the AND gate, I need to invert that 0 into a 1, right? So I've got inverters on those 2 inputs, right? So anytime you see a 0 in that truth table, put an inverter there so you get your 1. Okay? So I want that to turn on 4, which is 1, 0, 0. So I put an inverter everywhere that there's a 0. So that it'll become a 1, and then it'll open up that AND gate. Cool? It'll be coming on almost exactly. As soon as I get a 1, 0, 0, like it hits 4, this gate's coming on right here. And we can do something on the 5th step, right? All right. What about, what should 5 be? It should be non-inverted, inverted, non-inverted. So non-inverted, inverted, non-inverted. Y'all see what I'm doing there, right? Because the B is a 0. I want it to turn on when the B is 0 at that point. So I'm going to have to make that B a 1 to turn on the AND gate. Cool? 6. This is non-inverted, non-inverted, inverted. So A is already a 1, B is already a 1. We need to make the C a 1 to make the AND gate come on. 7. It's a 1, 1, 1. So if we have a 3 input AND gate, it's coming on with no inverters. And all right, so there's something we could do. Like right here on number 1, we could have an LED with the number 1 sitting there, right? So that when that LED comes on, we know that that binary number is 1. So we can make a binary to decimal converter by putting 8 AND gates with the different combinations of the inputs so that they only come on 1 at a time, right? Or like this function right here, y. We want it to come on when any of those come on, so we'll dump all of those into an OR gate, and if it's 1, 4, 5, 6, or 7, it's going to come on. Okay? How do we write that into an equation? All right, so we'd say A naught, B naught, C. That's all together for that first one. Or A, B naught, C naught. Or A, B naught, C. What would this be right here? A, B, C naught. And then this one would be or A, B, and C. We should be able, no matter what I gave you, if I gave you a circuit, if I gave you a truth table, or I give you an equation, you should be able to get the other two. Okay? Now, I want you to think about something. This is a little bit ahead of where we're at right now, but I like to seed that information into you. That's why I talked about the Morgans last week, so it'd be easier this week. We're about to simplify a whole lot of stuff. Okay? So y'all want to see that circuit simplified? All right, I can do it in my head. It's going to be so that big old circuit, we could do an OR gate with an A, and then would come out, and so with 1, 2, 3, 4, like each one of those circles is an inverter, right? That does the same thing. And I guarantee you, if you go in and do all that Boolean algebra, you would get the same truth table that we just did for this big circuit. Okay? How? I want you to start looking at things. Y'all remember on the circuit whenever we did the A or the AB or the BC? The A, if it was on, the output was on. Look at the A right now. Later on, we're going to figure out how to chunk these things together so that we can see where things like are combinations that we can get rid of stuff. If A is on, does B or C matter? Look at that truth table real quick. We've got A being 0, we got A being 1. Or no, we got B being 0, we got B being 1. We got C being 1, we got C being 0. We've got all the possible combinations that A and B could be, but if A is 1, I mean B and C could be, but if A is 1, we get a 1 out of there, don't we? Y'all see that? The last 4 ones? So there's a systematic way of combining things together and saying, okay, well, B and C doesn't matter in that chunk. So I can take all four of those and like all of this up here was combined down. Wait, all of this down here was combined down to if A is true, we're getting it out. And if you look right here, all four of these, like we've got four combinations of what B and C could be, but A is all true. Boo. Right? All right. So y'all got your laptop? Y'all got deeds? We're gonna do some deeds real quick. I want y'all to be able to if you've got 30 hours, well, you should be able to start this week even if you don't have 30 hours. Do what? Yeah. We'll I've got a little thing that I'll show up. Like it's a good rotation for everybody. Yeah. You still have that? Okay. For digital, this right here. All right, so I do skip around the book a little bit because the book skips around. So I skip around to de-skip the book. Okay. So pull up deeds. Everybody got deeds? Let me go get some drink while y'all getting deeds. What time is this class in? 2? What time is it right now? 2:50. Okay. Still got problems with it. We'll give him a second real quick. You got change too? Yeah. So if you're joining us online, you have to do it pretty much on your own, which you can get help from me, but yours what? You want to try another one? Like leave it up so it'll keep updating, or okay. Huh? All right. Is that showing up there? All right. All right. Up until this point, I would say you don't get to use a component until you build a component. Okay. And then the more I think about it, the more I realize I'm kind of wrong. I'm not going to let you use a component on your own until you can prove that you can build a component on your own. That doesn't mean that you can't use it the first time so you see what that component does. Okay? So, we're going to use our clock generator. So, go into your inputs and put the clock generator in. And we're going to use what's called a counter. What a counter does is every time it gets a low to high transition from that clock, it counts in binary up. It'll be like 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, up in binary like we've been doing up until this point, right? So let's prove that this works. So put the clock generator in and then put a counter in. It's going to be over here under counters. So there's 1, 2, 3, 4, 5 sections. and then it's about the middle of that fifth section. On mine, it's below that blue triangle, but hover over and it'll say counters. Then go down to counter, and let's do a 4-bit up. Okay, so click that. I'm going to zoom in a little bit. All right, so that little triangle right there means that it's edge triggered. That means that it doesn't look at a 0 and it doesn't look at a 1. It just looks at the transition between a 0 and a 1. Okay? That means that it happens real quick because it could be 1 for a whole second. Right? So it doesn't leave that open the whole time. It just looks at that little like transition. Okay? And we'll learn how to make edge triggered stuff. And if you follow along, and then you can, you know, catch back up or whatever. All right. On an input, if we've got a circle or a line over something, that means that it's a negative triggered, like a low triggered bit. Okay. So if we want it to be clear, we need to give it a 0. Okay. Now, a lot of times, if you don't plug anything in, it'll be floating, so you can't decide what that's actually going to be. So we're going to put a switch in here, like an input switch, just so that we can make it not cleared. So if it's got a 0 on there, it clears it, okay? So we'll have to turn that switch on when we want to output some numbers. Go ahead and connect the oscillator to the clock and the switch to the clear. Now, this has Q0 on the right. That works for us. If we saw this counting up in binary, we would be able to recognize binary, wouldn't we? We know how that works, correct? We know how that looks. So what I want you to do is I want you to take a wire on each one of these lines and kind of go out a little bit so that we've got more room with them. And then what I want you to do is I want you to take, all right, so we've had little test LEDs before, but let's do a 4-bit output LED array. So that's going to be 4 LEDs all in one little box, okay? Flip it over so that it connects to those wires. All right. Now, go to play. When it says to save it, name it decoder 1. Okay? We're not building a decoder yet, but we're about to. Okay? So nothing's going to show if that clock's not running and this clear is not enabled, or like that not cleared is enabled. All right. So flip that switch up and then go right click on the clock and get it running. That sure as heck looks like it's counting binary, doesn't it? All right, I'm going to explain how a counter works. How does base 10 work when we count? the first thing goes up 10 digits, and then the next thing goes up, and then it goes up 10 digits, and the next thing goes up, right? So every time we go to the left, we're dividing by 10. When we're in base 2, every time we go to the left, we're dividing by 2. Like, so look at how fast the first bit is going. The bit next, the least significant bit, the one farthest to the right. The one to the left of it is going half as fast as that one. The one to the left of that is going half as fast as that one. Also and also. So to make a counter, all we do is make a couple of divide by 2s, and we got a counter, okay? But what I want to show you is something a little bit more interesting, because I really want you to... Oh, garbage. I've got a meeting at 3:30 and 1200. Okay. Let me go tell it. So we're going to cut this out a little short. What time is it right now? 3:05.
Not the whole thing, just the thing that's registering one year.
That's LED. LED like array support bit.
All right. So I'm going to make this a little bit bigger of what we're going to do. And then when we come back, because I've only got like about 15 minutes, we're going to break this down. And what we're going to do next class is to make it from scratch. Okay? So we've got a little counter that's counting up from 0 to 15. Okay? What that does is it gives us unique things that we can trigger things to happen at a different number. Y'all remember that truth table that we did? We can, have it happen at different times. All right. So have y'all seen a 7-segment display? Go to output, go down to 7-segment display, and go to 1 hex digit. Okay. Cool. And then put that over here. And then wire it up so that the least significant bit, like that dot right there, goes to the same one that has a dot right there. And you just go foop, 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 foop. And then play it. Turn that clear off. Okay. The reason I'm letting you do this first is because I want you to realize the magic that you're about to do. Because we build this from scratch out of nothing but ands, ors, and nots. But by the time you get there, you're kind of like, oh, well, that's cool, but like, that's not amazing. I want you to remember how you feel looking at this circuit. And would you think that you would be pretty smart if you could build this out of nothing but ands, ors, and nots? I want you to remember that, because once we get done, you'll be like, oh, that was simple. But you got to realize that it's really not. And it really is, and it's really not both at the same time. It's really impressive, like, to be able to build it from elemental gates. But you're gonna do it easy enough that you're not gonna realize how smart you're getting. All right. So what time is it? 3:07. I really wanted y'all to make me a gate or a circuit that would spell out ROB. Okay. So we're going to look at decoders, which when you decode something, you're taking information that's in something and putting it into a format that you can understand. So we're taking ones and zeros, and then we're making it right there. That's just 7 LEDs that are shining, right? And they put it in a way that we could see it to represent a number or a letter, right? So we're decoding that binary into something that's readable. We also encode. So if we wanted to turn a letter R into something that the machine could understand, would convert that into ones and zeros. So we're taking ones and zeros and making something that is human readable as a 7. So we're decoding that, right? But let's see how fast we can do this. On 0, I don't want anything to happen. On 1, I want an R to happen. Okay? I want a lowercase r. So this middle segment and this left segment. Okay? We're going to spell out my name, R-O-B. All right? Cool? All right, so let's leave that in there, but let's take a 7-segment display, 1-digit unencoded. All right, so these are just the LEDs, okay? I can easily make it so that on the first step, an R shows up, okay? So step 2, 0, 1, okay? So what's that going to be? Like if it's the first step, then it's going to be 0, 0, 0, 1, right? So this one will be 0. Let me get off of here. This line will be 0. This one will be 0. This one will be 0. This one will be 1, right? And I want this middle segment and this left segment to come on, okay? So let's take an AND gate, and it needs to be a 4-input AND gate, okay? The only one that's not inverted is this first one, right? All right, the rest of them need inverters in them. So we're going to knock a inverter. I have to stagger them because that's hot garbage. They won't let you put them close enough together. So let's pull this back a little bit. Let's kill this. This one's going to go up. To the second row. I want to stagger them like this so I can get them all connected. Which I didn't need that third one. This one's going to have to go all the way back to this third row, right? And then this one now, when I'm not crunched for time, we'll make this a lot prettier, right? So we've got those. So whatever's going to come out of here is only going to come out on the first on number 1. So let's go ahead and put a test LED right there. All right. So I want something to happen on step number 1. Go ahead and play that. Turn on your thing, turn on your animation. So only on step 1 is that going to be true, right? Oops. Big old head. All right. Only on step 1 is that going to be true. Y'all see some power here? Could we not make a gate for every step that we want? So we could have a gate that only turns on step 0. That would be all inverters on it, right? Because every input is a 0. So we'd have all the input 0 with the inverter on them. Then that would turn on step 0. Okay? We're about to make a decoder that's decoding binary into decimal. So it'd be like 0, 1, 2, 3, 4. And then we'll take that and we'll make a 7-segment decoder so that whatever step we're on, it converts it so that certain LEDs come on to look like a 0 or look like an F or look like an A. Okay? But this is the start of it. Okay? I could look at it and let's say that I want it to spell out ROBB, right? I could look at this and say, what step is G going to be on? G is going to be on steps 4, 5, and 12. Okay? What I do want y'all to look at all right, so look at page 325. It's not up yet, okay? But I want y'all to read it.
So do I need to submit this for the lab tomorrow?
Yeah, this one will be fine for the lab for this week. But y'all need to have this saved so that y'all can work on it some more next week. Okay? Because I didn't quite have the time that I thought I did. But do me a favor. This will prove that like people watch the video. Go ahead and read up on encoders, which is 6.6. Okay? Starting on page 327. No, I don't want encoders. I want decoders. Decoders is 6.5, starting at 317. I want you to give it a good college try. So that I want y'all to come in. I'm not giving you any homework on that part. There is some homework from Karnoff, or not Karnoff, but DeMorgan's. Give it a good college try so that whenever we come in and talk about decoders, y'all show me that y'all actually read it. And then, like, if y'all do that, then the homework gets really small, right? Okay. Y'all have a good time. But if y'all get at least this much, if you get this much built, then that's where you're going to stop for this week. But keep that saved because we're going to build on this and it's going to take up a good amount of that screen.